All right, let's get started. I know it's a little bit of a chilly day, but it does seem to be pretty nice in here. So, and also welcome back. Apologies for canceling on Monday. Of course, I had traveled Monday through Wednesday of last week, and then we had our technical conference on Thursday. Friday, if you recall, I was feeling a little under the weather. I thought it was just from being exhausted from having a busy week and maybe coming down with a little bit of a cold. Nah, at that point I decided I think it would be a good idea to come down with a case of the flu. So, yeah, on top of all of that, I was like, yeah, let's just add that up on there. So, I've been, yeah, it's been a rough couple days, but I'm back. Still a little just tired and whatnot, but I'm good to go. Homework 1 is due today, so got a pile started right up there. Homework number 2. So homework number 2, I want to say something about that. I have it due on Wednesday. I might push that back because we're, where I missed on Monday. Like if I hadn't missed Monday, we probably would have just kept on trucking and we'd be fine with it. There's a chance I push that back. And there's a homework in steel. That one's due a little later, and I actually think we're going to be fine on that one, but we'll see. So basically, let's put it like this. Monday, let's revisit that that due date. So, but I'm going to try and just book it because I kind of want to get us back up to speed. I have some makeup days in the schedule, and I'm challenging myself to not use them. So I just want to book it. So I just want to get right back into where we left off last time and just get rocking and rolling. So with that, let's do just that. Oh. So, I know it's been a while since we've met, but let's get back to square one. We were talking about beam behavior, and this is sort of where we left off, the concept of a cracking moment. Okay? Does everybody remember this? So we have the moment of inertia, the extreme fiber distance, and then the modulus of rupture that are utilized to compute the moment at which a beam will first experience cracking. Okay? And what we did is we said, all right, let's look at this problem right here, okay? And we determined the stresses under a 25-foot kip moment, and then we asked, well, what would be the moment that causes it to crack? And we determined that it was really, really close to that 25-foot kip moment, just a little bit higher, ended up being like 25.6. So today, what I want to do is I want to ramp it up a bit. I want to talk about this beam, okay? Now, one thing that if you noticed in the last problem, the one thing that we didn't utilize was the rebar. It didn't matter. So since it didn't really matter for this problem, that was sort of a point I was making. It'll matter later, believe me. But it didn't matter for a cracking moment computation, so I want to determine the cracking moment really with this problem. And we have 3A and 3B. We're going to take this same problem and we're going to do a few more things with it. So example 3A, what I want to do is I want to determine what are the stresses if we just put it under a positive bending moment of 80 foot kips. So it's a lot like what we did in the previous example. And then in 3B, if we have 3 KSI and normal weight concrete, what's the maximum uniformly distributed load the beam can carry before it exceeds its modulus of rupture? And so we'll get to that here in a second. The one thing I want to mention before we get started is 2 things. Well, I say one thing, and I have 2 things. First off, if you notice, I've thrown in a little bit of additional notation. So this term here is H sub F, and that's if you want to think of the height of the flange or the thickness of the flange, that's basically how thick this element here is. I'm using the term H sub F. We will always use the term H sub F in this course, so I'm sort of slowly introducing you to some of that notation. And if you notice, there are also 2 B values. There's a B of 60 inches and a B of 12 inches. The B of 12 inches, that's B sub W. That is the width of the web. So they use B as an abbreviation for breadth, but I've never really heard anybody say that. People just say width. So that's the width of the web, and then B is just the overall width of the flange. So we don't really use B sub F. So okay, sound good? And that term 27 doesn't really have a name. What we would normally do is just measure the entire height of the beam and say it's 32. So I just made it simpler and just went ahead and reported 27. All right, sound good? All right, so that's the first thing I wanted to note. The second thing is the actual shape of the beam. Before, the beam looked like this. So what was the moment of inertia of this beam? Like, how do you compute the moment of inertia of that beam? Yeah, exactly. Yeah, pretty straightforward. BH cubed over 12. What about the moment of inertia of this beam? You got to do a little bit more to this one. Okay, so this is something that you did either in statics or mechanics of deformable bodies. Quite frankly, it could happen in both courses, but we're going to sort of recap that. I'm going to show you sort of my way of doing it. But remember, in order to compute the moment of inertia, you need to determine where the centroid is. You need to determine effective distances and whatnot. So we'll go through that step by step just to make sure everybody is okay with that. So give me a second. Oh. Sorry, I just think that's cool. Okay. All right. So what we've got is here's our cross section, and remember it's subjected to a bending moment of 80 foot kips, but we'll deal with that later. Right now, what I want to determine is the parallel axis. So, or basically what I'm going to be utilizing is the parallel axis theorem. So, let me sort of recap everybody on that. So if you want to determine the moment of inertia of a composite shape, and when I say composite shape, what I mean is a shape built up of a bunch of simple shapes. So for those of you who are in bridge engineering, but for those of you who are in senior design this morning, I'm not talking about composite action in the same way. I'm just saying, like, this is a shape that's composed of, let's say, two rectangles. That's what I mean by composite shape. So to determine the moment of inertia of a composite shape, what you do is you sum the following quantity. You say, I'm going to sum up the moment of inertia of each individual little shape plus the following quantity, AD squared. Okay? Now, area, A is just the area of each individual shape. D, we'll get to that here in a second. I don't want to get overly convoluted, especially when this is a review, but don't worry, we will get there. Now, the first thing that we have to do is we have to compute a centroid, okay? So a centroid, if you recall, so actually here, let me set the stage a little bit better on that. So the centroid is something like, let's say, y bar. Do you remember this? Remember that? Sum of AY over sum of A? I have got to believe that you've seen that calculation at some point or another. Everybody okay with that? Now, what I like to do when I'm computing a moment of inertia for a shape like this where it's composite is I like to draw basically one big table and do all the calcs in one solid chunk. So I'm going to show you how I do that. Just so you're aware, I'm going to draw a table down here, and there's going to be like 7 columns. So if you're writing this out on your notebook paper and whatnot, just be prepared for like 7 columns. Okay. Now, before I do that, I want to go back to that centroid calculation. Remember, when you compute sum of AY over sum of A, your Y distances all have to be referenced from the same point, right? So at the very beginning of your computation, you have to define what's called a reference datum, a common axis by which you'll reference your distances. And so for shapes like this, usually I say that the bottom is the datum. So what we'll say for our purposes is that the datum is here. And so what we'll do is we'll split this, let's say, into 2 simple shapes for the sake of discussion. So I have a T-beam, right? So what I might do is I might say, okay, let's split that up into two rectangles. So we'll say that this is rectangle number 1, and this is rectangle number 2, okay? You could split that up however you'd like. You could draw your lines here and here and say this is rectangle number 1, and that's rectangle number 2, and rectangle number 3. You could do this however you'd like, and it'll still work. I just think that's the easiest way to do it. And then for each of those rectangles, we'll locate where the centroid is. So would you agree that, let's say, for rectangle number 1, the centroid of that rectangle is probably going to be somewhere about right there? Would that be a fair statement? And then for rectangle number 2, maybe about right there. Everybody okay with that? That's not too bad. Okay. Sound good? All right. So now we're ready to start drawing our table. Okay. So, like I said, I'm going to have a big table down here. And forgive me, it's going to have quite a few columns. It'll have 7 columns. Okay, so the first column over here, I'm just going to put the shape. So there's going to be shape 1 and shape 2. And so if you had an I-beam, there might be 3 shapes, you know, top flange, web, bottom flange, you know, whatever makes sense. Okay. Then next, we're going to put the area. Okay. So let's start off with the area. So let's take shape number 1. What is the area of shape number 1 in square inches? It's 300, right? 60 wide, 5 tall, right? So it's 300. Pretty straightforward. Okay. What about shape number 2? What's the area of shape number 2? 324. Got a second on that? Okay. Next thing I'm going to do is here on the bottom, I'm going to put a sum here on the bottom. So 300 plus 324, I'm going to say that that is, what, 624? All right. Simple, right? Okay. All right. So if I'm computing centroids, I've got A's, I need Y's, right? So I need Y distances. So what are the Y distances? The Y distances, keep in mind, they are measured from the datum. No, from the datum. Then that's the critical point, okay? They're always measured from the datum. So let's take this first one, okay? You said 2.5, but 2.5 is measured from here. All of your distances have to be measured from a common reference point. So how far is it from the datum to the centroid of shape number 1? It's not 2.5, it's 29.5. There we go. All right. Now we're rocking and rolling. Okay. What about the next one? Okay. How far is it from, excuse me, how far is it from shape number 2 to the centroid of the whole thing? Say it again. There we go. Sound good? All right. Now what we can do is we can compute AY quantities. So AY quantities are pretty straightforward. We just take each of these and multiply them by one another. So what is A times Y? A times Y. Somebody give me the first one. 8850. And the second one? 4374. Do I have seconds on these? Cool. Now let's add them up. Sum of AY over sum of A. So let's sum them up. Say it again. 13,224. There we go. So what I can then do is I can say now I can compute my centroid. So up here, what do we have? Sum of AY over sum of A. just divide these two. So, I think do better than that. And see, look at your units. That's 13,224 cubic inches divided by 624 square inches. So the answer is going to come out in inches, and it's going to be what? We'll say 2 decimal places, just to keep it simple. 21.19. Second? All right. So what that means is that from the datum, if I go up 21.19 inches, that will give me the centroid of the whole thing, right? So the centroid of the whole thing is about right there. Maybe I'll draw that out. Okay, so just so you're aware, what you might see me draw on some schematics like this is you might see me say, okay, here's this line. This right here is y bar is 21.19, but you might see me write NA. Everybody know what I mean by NA? The neutral axis. So that's the neutral axis, okay? So the neutral axis is where the centroid is located. So if you ever see NA, that's what that is. Sound good? Okay. Now, let's go to our parallel axis theorem. Now, the parallel axis theorem is really what we're trying to do because we need a moment of inertia of this whole thing. Okay? Now, the parallel axis theorem states that we need 3 quantities for each of these shapes. We need an area for each of these shapes. We got that taken care of. That's no problem. We've got a moment of inertia, this I sub naught. Let's take care of that first. All right, let's take care of this. So let's draw ourselves another column. And let's write in our I sub naughts. Okay, now, this is where you got to pay attention. Remind me, what is the moment of inertia of a rectangle? Because ultimately what we've got here are 2 rectangles. Say it again, BH cubed over 12. But let's be clear, B times H cubed over 12. So it's the width times the height cubed. So what's the formula going to be for shape number 1? There we go, 60 times 5 cubed over 12, not the other way around, because the width is 60 and the height is 5. Excuse me. So this is going to be 60 times 5 cubed divided by 12. And that's going to equal what? Say it again. 625. Now for the bottom one, for shape number 2, what's it going to be? But what's the formula? There we go. 12 times 27 cubed. And so your 12s cancel, so it's just going to be 27 cubed, and that's going to be 19,683. Is that what you said? Do I have a second on that? Okay. Okay. All right. Bless you. So going to the parallel axis theorem, we need I naughts. We've got those. We've got A's. We've got those. We need D distances. Okay. Does anybody remember what those D distances are? It's okay. I know it's probably been a while. Oh, you can go. That's exactly right. So now you're talking about distance to the rebar. You're talking, or who said distance to the rebar? That would be, if we were looking at the structural capacity, you'd be exactly right. And I could see where the notation would be a little confusing here. Here, what we're talking about is how far is it from the centroid of each little shape to the centroid of the whole thing. Okay? So here's a simple way of computing this. It's actually a lot easier than you would think. Okay? So look here at the cross section just for a second. And I'm just going to use shape number, I'll use shape number 1. So how far is it from the datum to this? What did we say it was? 29.5. And how far is it from the datum to the neutral axis? 21.19. So how far is it between those two? How would you do that? And how did you do that? Just subtract them, right? So I propose that in order to determine these d distances, the way that you would do that is you would say each of these little y values minus the y bar for the whole thing. Now here's the interesting thing. You got what? What'd you say it was? 8.31. Now what if you did the subtraction the other way? What would you get? You get negative 8.31, right? Would that really matter in the end? Whether you subtracted y minus y bar or y bar minus y, would the order really matter? Because it's squared, so it doesn't really matter. So I'm usually pretty loose on which order you subtract because you're going to square it. So what's the second one going to be? Just to be consistent, if we'll do it the same way. So this one would come out negative. Negative 7.69. Do I got a second on that? Pretty simple stuff, right? So now what we can do is we can compute I naught plus AD squared. And so we'll take our time on that, but ultimately we're going to say this plus that times that number squared. So it'll be 625 plus 300 times 8.31 squared. And so what does that yield? Say it again. 21,341 point, so we'll say 0.8. So 21,341.8. Do I have a second on that? All right, and now for the next one. Excuse me. 38,000? And you said 843.1. Do I have a second on that? Okay, so sum those up and what do you get? $601.84.9. Sound good? Any questions? So what does that mean? Here's what that means. Let me scroll down a bit. I propose that the gross moment of inertia is 60,184.9 inches to the fourth. I propose that YT is 21.19 inches. Now I'm curious, for the sake of discussion, what would YC be? Just see if anybody can follow along with that. Remember, what is YT? It's the distance from the centroid to the very, 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 very bottom. So how would we determine the distance from the centroid to the very, very, very tippy, 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 tippy top? How would we do that? Now here's the beam. Yeah, so 32 minus that. So what is that? Say it again. 10.81 inches. Everybody okay with that? So here's the reason I asked for that. Here's the beam, right? And we say that the neutral axis is about, what, about something like that? Is that a fair statement? Okay. Well, remember, we have a bending stress profile that we'd like to consider. All right? And remember, bending stresses are 0 at the centroid, and then the farther away you get from the centroid, the larger they get, right? So what's going on with your bending stress profiles, it really looks something like this. Now, these are the stresses in compression, and these are the stresses in tension. I can do better than that. There we go. I think that's a little better. And so this value right here, that value right there, we might call that F sub tension. And what we might do is call this value right here F compression. And I'm making it a point not to call it F sub C because I don't want you to confuse it with S sub C prime. So that is the bending stress in compression and the bending stress in tension. Okay? Now look at my scale. Which one looks larger, the tension or the compression? Tension. And that should make sense because remember, this distance right here, that is Y sub T. That's that extreme fiber distance, and that's 21.19 inches. This is the extreme fiber stress and compression, so we'll call it Y sub C, 10.81. Sound good? Now, remind me, what was the bending moment on this problem? $80 kips, right? Now, 80 kips, that, anybody see a problem? Anybody see a problem right here? All the units are in inches, but the bending moment is in foot kips, right? So right off the bat, we probably ought to convert that to inch kips. Now, how do you convert foot kips to inch kips? What do? Multiply by 12. It's feet and inches, right? So what's 80 times 12? 960. Okay? Now, you could stop here, but just for the sake of discussion, I'm going to convert this to inch pounds. So I'm going to multiply by 1,000. I'm going to say that this is 960,000 inch pounds. All right. And so therefore, our bending stress in compression, and so we tend to use the letter F for stresses in concrete. So bending stress, you probably used to sigma equals my over I, which is just my over I. So we're going to say m times y, in this case yc, over ig. And so that is 960,000 inch pounds times 10.81 inches divided by, was it 6,000 or 60,000? 184.9 inches to the fourth. And so you notice if you draw all this out, you will see all the units. Again, write it out. You know, actually spill out. Write IN with the little 4 as an exponent on top of it. IN dash LB. Actually write it out, and you will see that all of the units are consistent. And so what does this come out to be? We'll say 172.4 psi. Now what about for tension? Now, what's the difference? Like, what's the only thing that's going to change? Use YT instead of YC. So I'm not going to rewrite that formula. I'm not going to rewrite all that out. So I'll just say that. And so tell me what that comes out to be. So we'll say 338 PSI. Do you have a second on that?
Yep.
And so the problem was asking for the top and bottom extreme fiber stresses under 80 foot kips, and so that would be your answer right here. Now this is a straight engineering 216 problem through and through. So this actually really isn't much concrete design, but yes?
Okay, well, this might be from 216. How did you get that graph?
Get what graph?
The graph right there with F compression, and how do you know which one was compression?
Because that's a great question. We are assuming that this is undergoing positive bending, okay? I think that was stated in the problem, wasn't it? Did it say positive bending? Okay, so in positive bending, remember, positive bending is when the beam acts like it does a smiley face, right? So the top is in compression and the bottom is in tension. As for the graph, this is just fundamental bending. Anytime you have something being bent, and that's it, just being bent, there is zero bending stress at the centroid, and then it's just linear from the centroid. So your highest bending stresses are going to be at the very, 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 very top and the very, 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 very bottom. Now, when we did our last problem, the last problem was a rectangle, so it was symmetric, right? So this centroid was right smack dab in the middle, right? So the bending stress on the top and the bottom were the same. In this case, they weren't, because the centroid wasn't in the middle. It was 21.19 inches from the top. Does that make sense?
How do you know to make your line that way instead of the other?
I usually just put compression on the left because we usually take compression as negative. And so tension on the right, taking it as positive. There's nothing really special. You could flip it, it wouldn't really matter. The numbers and the sign doesn't really matter. In my opinion, what matters most is that you understand the context. So when you say this 172.4 PSI, do you understand that that is in compression and that this is in tension? That's what's important. As long as you understand the direction of the stress, that's what's most important. I'm not going to get hung up on whether it's positive or negative. I'm getting hung up on whether or not it's compression or tension. It's like what we did in truss analysis last semester. If you remember, we always assumed tension was positive. I mean, we did that just to make some of the math easier, but it really didn't matter. We could have assumed compression positive, and we would have gotten the same answers, just flipped. The context mattered. So, does that make sense? Is everybody else okay with this? These are good questions. So, any others? This is good stuff.
Even if we didn't know that it was undergoing positive bending, we didn't know just because it's a shorter distance the top was compression?
Well, not necessarily, but the shape of the beam, I would think, tends to lend credence to the fact that it would be undergoing positive bending just because it looks like this beam has like a large slab on top. So you would think that the load is being put on top as opposed to the bottom. But that's not always the case. I mean, I'll say this, more often than not, as the engineer, you're going to know whether or not it's going to experience positive or negative bending just because of the structure. To give you an example, if you're designing, let's say, a two-span bridge, okay, you got an abutment, you got a pier right in the middle. Well, right there over that pier, the bridge is going to want to do that. So it's undergoing negative bending. So that region, your reinforcement and your design is different than out, say, in the main spans where it's wanting to smiley face a bit. These are good questions, so this is good stuff. Yes?
And this isn't the stresses that's going to crack. This is just when it's under 80 foot kip.
That's exactly right. Let me ask you a question, follow up on that. The last problem had a normal weight 4 KSI concrete, right? So what was FR for that problem? What was the modulus of rupture? was 474 psi. Everybody remember that? So if this beam was made out of normal weight 4 KSI concrete, would it crack under these loads? No, we're not quite there yet, right? It's what, 338, right? Would we look at this number if we were trying to determine whether or not it would crack? No, we would look at this one. Remember, the modulus of rupture is the point at which the tensile region cracks. This number doesn't really matter if you're looking at cracking. It's this number that matters. You're checking the tensile stresses against FR, not the compressive stresses. Does that make sense? All right, are there any other? This is good stuff. So. Yes?
Is there any like factor you would use the compressive stress as a baseline for? Like how we use the tensile limit right there to tell whether it's going to crack or not. Can we use the compressive stress to tell if it's going to act a certain way or not?
No, but we've got a lot farther to get in terms of what happens after it cracks. Because just because the tensile region cracks does not mean that the beam is done by any stretch of the imagination. In fact, if you look at the cracking moment of a beam versus its actual nominal flexural capacity, they're nowhere near the same. So beams can handle a whole lot more beyond cracking moment. So we're just getting to the, like, this is like stage 1. So but the way that we handle that is different, and I don't want to confuse you, but we're going to get there. So because there's like a stress block approach and all that. So anything else? You will, but the way that we handle ultimate capacity is we assume that so just so everybody is aware, when you're looking at ultimate capacity, this is how we assume the behavior of the concrete. We assume that all the concrete in tension is gone. We just assume it has zero capacity at all. And we assume that the concrete in compression has reached basically full FC prime, like all, but the problem is that by assuming it reaches full FC prime, you're assuming a nonlinear stress distribution. So how you account for that simply takes some discussion. So we'll get there, but everything in tension we just assume is gone. So it does, I mean, you do get crack propagation, but we just conservatively say, oh, it doesn't exist. So yeah, you can't really count on concrete if it's like that. Anything else? This is good stuff. All right, let me go back to the slideshow because I do have there's like a follow-up to this. It's a little bit shorter, but I want to make sure everybody's clear on this. So let's say this is sort of taking what we did at the end of example 2 and extending it forward just a little bit. So this one, let's say we have 3 psi or 3,000 psi normal weight concrete, so not 4,000. So we're not quite. So the concrete that we're using here is a little bit weaker, okay? But we are still using normal weight concrete. But I'm asking something a little differently. I'm asking, what is the maximum uniformly distributed load that this beam can carry if it is used as a simply supported beam without exceeding the modulus of rupture? So this one is a little bit more involved than the problem that I asked last time, but we're sort of getting into a little bit more of a dose of reality. So I'm going to comment on something here in a second. So everybody got this? Okay, so let's look at example 3b. So first off, we were told in this example that we have 3,000 psi normal weight concrete. So if we know that FC prime, if we know that FC prime is 3,000 psi, and we know it's normal weight. Now, first off, what does that normal weight tell us? And what lambda do we use if we have normal weight concrete? There we go. And so why does that matter? What does lambda and FC prime give us? There we go. FR, which is 7.5 times lambda times the square root of FC prime. So that is 7.5 times 1.0 times the square root of 3 KSI, right? There we go, making sure y'all are paying attention. You're like, it's too cold, Dr. Mike. We don't do this to us. Like, you see us writing like this with our pencils, now we have to erase. So what does this come out to be?
410.79.
Okay, so we'll call it 410.8 PSI. So I'm just curious, would the beam still have cracked under that 80-foot kip moment on the last part? No, because what was the tensile stress? What was it, 330 something? 338. So we still hadn't quite have experienced cracking. I mean, it can handle probably a little bit more if I'm guessing something like 100, 110, something like that. So, well, speaking of, how could we determine how much bending moment it could experience? Maybe we could occur, or maybe we could calculate its cracking moment. How do we calculate its cracking moment? Well, we need IG and YT, but lo and behold, we have those from the previous example. So therefore, we can compute the cracking moment pretty easily as just FR IG over YT, and so that is 410.8 PSI. We have, excuse me, we have, what was the gross moment of inertia? It was 60,000. There we go. And then we have YT, and I think that was like 21.19. Okay, and so what does that come out? Was that a glitch in the matrix? I don't know. It did. Nothing happened here on the screen. I think that was just the HDMI. Did I give it the flu? That's not funny. That's good. So what does this come out to be? Now keep in mind, it's going to be a real big number. 1166774. 2. No. Now, what are the units? Remember, it's a moment. Remember, a moment is a force times the distance. There we go. Now, that's kind of big, so maybe let's scale that down a bit to inch kips. So we'll say 1166.77 inch kips. And scale it down a little bit further. Let's divide that by 12. I might need some help on that one. I'm not that good.
97.
So 97.23 foot kips. So I was guessing a little lofty. I need some help with my mental math this morning because we had 80 before, and so 97. I think I said like 100 or 110, but 97 would cause it to crack, right? Now, but that's not what the problem is asking. The problem is asking how much load would cause the beam to crack. Now, what does it say? It says how much load would cause the beam to crack if what? If we had a distributed load on a beam that's how long? 24 feet. Okay, so let's think about that for a second. Now, based off that last homework that you all just did, you should probably be able to tell me that if you have a simply supported beam with a length of L, what is M max? It's not WL squared over 2, over 8, right? Now, did anybody look at that guide that I posted? It was in the design guide, design aids and supplements. Did anybody look at that? Here, we got time. Or if I can pull that up. You can do a moment diagram, that's fine. So if you go into concrete design, I'll go into student preview, so looks like what you all see. If you go into course content and you go into lecture notes and supplements and you go into the design aids, the first link will show you design formulas for shear, moment, and deflection. Did I show you all this? So if you go, let's say, to figure number 1, simply supported beam, uniformly distributed load, M max. Gotta look at the website a bit. My goodness. But yeah, I mean, you can use statics and structural analysis, whatever you'd like. But yeah, the maximum moment is W all squared over 8. So what you can do for this is you can say, all right, I know that the length is what, 24 feet, was it? So I can solve for what is W. So how do you solve for W? What do? You take 8 times M divided by L squared, right? So therefore, what we might say, now keep in mind, we're not doing any load factoring or anything like that right now, so let's just keep that in mind. So I'm going to say, therefore, that the cracking load is 8 times the cracking moment over L squared. The reason why this formula works, though, is because it's a simply supported beam. If it was a cantilevered beam and it would be WL squared over 2, the formula would be different. It would have a 2 there. So is everybody okay with that? Now, let's see. So that's 8 times 97.23 foot kips divided by 24 feet squared. And so WCR equals what? Now keep in mind, this is a distributed load. So how do we express, like, what are the units for distributed loads? Like kip per foot. And so what's the answer come out to be? 1.35. Do I have a second on that? Now, before I hit, circle on that, there's something that we need to keep in mind. Is there something I'm forgetting? Is that how much load I can put on top of that beam before it cracks? No, hold on. Let's think about this. Here's the beam. The self-weight. The beam itself has weight to it, right? How do we determine how much the beam weighs? Ooh. Oh. How do we determine how much the beam weighs? Well, we don't really have to worry about that because we can assume that the beam is reinforced, so we can assume a unit weight. You're on to something. How do you we had this formula in our notes. How do you determine the self-weight of a beam? The specific weight times the area. Y'all remember that? It's in there, I promise. It's like somewhere around slide 60 or so. But what I will do is this. I will say that this 1.35 kips per foot, that includes self-weight. And we can, for now, go ahead and call that the answer. But I'll put a note here on the side. And I'll just say, I'll put a note right here. I'll say if the unit weight of concrete is 0.15 kip per cubic feet, and the area of the beam is what? What did we say the area of the beam was? Didn't we compute that in the previous section, like when we did all our tabular calcs? 624 what? Okay, so 624 inches squared. How would we convert that into feet squared? Say, divide by 144, not 12, by 144. And so if you divide that by 144, what do you get? 4.3 even? 4.33 feet squared. I'll say, therefore, the self-weight of the beam is gamma CAG, which is what? What is 0.15 times 4.333333 repeating? .65. So 0.65 kips per foot. So the beam can withstand 1.35 kips per foot before it cracks, but the beam is already experiencing this much load due to its own self-weight. So how much can we put on top of it before it cracks? 0.7. So the beam can hold up 700 pounds a foot before it's going to crack. So what do you think? So the big thing is I just want you to keep in mind all these details as we move forward. So everybody good? That's all I got. We're going to talk about transform sections next time, and after that we'll start looking at flexural capacity. But basically, just so you're aware, next time we're going to talk about what happens when the moments exceed the cracking moment. If you haven't turned your homework in, do so. That's all I got.